Yes, my speech today really is about not just about advanced materials really, but about the barriers that we're going to have to overcome to ensure that we can use these in our future factories. So what are advanced materials? Well, they cover a wide range of substances, everything from metals, as we've just heard, ceramics, gels, polymers and composite materials. They are generally designed to outperform traditional materials such as steel and aluminium, and they lay claim to some superior properties, including greater toughness and high temperature strength. And even more importantly, these materials can be tailored to support particular applications. In fact, they have been known to enable new technologies to be developed outright. The real mark of an advanced material, however, is its role in product design. It enhances component performance and indeed entire systems such as cars and spacecraft, allowing more compact designs, improved fuel efficiency and greater durability. And if we add smaller into that list, then individual material atoms are now being manipulated to make new materials in the burgeoning field of nanotechnology. And carbon nanotubes, as I'm sure you've all heard, possess 100 times the tensile strength of steel and about 10,000 times finer than a human hair. The promise of product enhancement and new technologies sounds great, but actually delivering them is another matter. The transition from laboratory wonder to commercial success is long and arduous, but through research and innovation design, several materials such as carbon nanotubes, magnetorheological fluids and shape memory alloys are making slow but steady progress into the market. So why are these materials so important to the manufacturing community? Well, innovative materials technology make a direct and positive impact on economic growth through improved processes and products throughout their life cycle. UK businesses that produce, process, fabricate and recycle materials have an annual turnover of around £197 billion. They form a critical element in the high-value manufacturing supply chain. Innovation in advanced materials development and application is strengthening the UK's world-leading position as a provider of high-value added products, processes and services, which have the potential to bring sustainable growth and high economic value to the UK. And indeed, in 2013, David Willits invested £45 million in advanced materials research in areas such as composites, high-performance alloys, low-energy electronics and telecoms, and materials for both the energy and health markets. However, uncertainty in the future availability of energy and raw materials puts at risk the development of high-value products and drives up the cost of materials for a wide range of businesses. And a survey that was carried out in 2011 found that around 75% of European entrepreneurs have seen the cost of their materials rise over the last 5 years, and indeed 87% expect that to continue to rise over the next decade. There continues to be societal concerns then really about the availability of materials and about the environment, natural resources, security of energy supply and fuel poverty, and a demand for materials and related processes that can use less energy and incorporate renewable materials. Advanced materials technology can and will address these challenges, particularly facing the energy industry, in areas such as power generation, transmission and storage of energy. And there is certainly an appetite to develop novel materials with improved intrinsic properties, utilising existing resources in high-value products for a wide range of applications. So what kind of advanced materials are there? Well, since I've only got 20 minutes, it's a bit difficult to go into that, and we'd probably need an entire conference just to talk about advanced materials just on their own. So I've chosen to select 4, actually, that I thought might be of interest to you, and you might not necessarily think as being advanced materials. The first of these, I'll just jump through that, sorry. The first of these is fungal foam. Now, you think, okay, fungal foam, what's fungal foam got to do with an advanced material? Well, it was initially conceived as a cost-effective, environmental-friendly and high-performance alternative to styrofoam. It's made from agricultural crop waste, and it's bonded together with mushroom roots, the mycelium, the fine structures that you see on mushrooms. It's now being used as a biodegradable alternative to petroleum-based plastic foams, such as those that are used in the automotive industry, in car bumpers, dashboards, seats, that sort of thing. And it also has the opportunity to be in more household-related products, such as tabletops, surfboards, even clothing. Electric ink, or samarium hexaboride, I think that's how it's pronounced. It's actually quite a little-known compound that was discovered in the 1960s. But it shows some very interesting properties, topological properties. And this means that if you make it in a thick enough layer, actually it acts as an insulator on the inside and a conductor on the outside. I'll give you a second to think that one through. It doesn't really make sense. It's unaffected by impurities that normally hinder electron motion through other materials, and it adheres to any surface. So it can actually be printed at low temperatures just using a standard desktop printer. Metal-free conductive inks will play a really important role in making printed electronic circuits for display screens, sensors and batteries in the future of our smart factories. Now, here's another material which I think you may or may not have heard of over the last few weeks. It's certainly been making an impact in the media. Self-healing polymers. These incredible substances are the latest thing in advanced materials. These kind of materials behave kind of like blood, actually, in the way they behave. When you rupture a surface, the liquid polymer oozes out, it leaks out over the surface, and by either means of heat, light, or other chemical reactions, it actually fills the gap, hardens, and forms a new skin. Self-healing materials like this would be incredibly useful in many places within our manufacturing industry. They could reduce costly downtime in factories where repairs might be either too dangerous to make or the environment too extreme. And my final choice of material are surface coatings, and we've certainly heard a bit about those from some of the other speakers. Recently, 2 universities in America have designed an extreme duty iron-based glassy alloy coating for industrial drill bits to make their equipment more resistant to breaking under heavy loads. This, what they're terming nanoshield coating, requires a laser to fuse the alloy powder to the surface of the cutter. The coatings cost far less than conventional materials such as tungsten carbide or cobalt, and their longer operating life improves the efficiency of the drilling process. But there are 2 materials that, as Lee alluded to, that have really been very much in the public eye of late. And whilst they have very different histories, they have common issues, and it's these I'd like to talk about now. The first of these is graphene, and yes, it is possibly one of the thinnest and strongest materials ever isolated, although I believe it's got a few more cousins on the way now. It's 0.33 nanometers thick, and almost 1 million times thinner than a human hair, and was obviously developed at Manchester, as we're all aware, back in 2004. The other material is composites, actually, and composites cover a wide range of materials, and actually there are numerous natural composite materials around, but really the mass application of them came around in the 1940s, and their application has been growing ever since through the last few decades. And in terms of applications, well, it could be considered limitless, really. Graphene has a major applications in batteries and energy storage, photovoltaic cells, flexible circuits, and composites have been used for many years in aircraft fuselage, in rail track equipment, and pipeline fabrication. Yet both of these materials, both new and old, are suffering from similar issues when it comes to the development of mass production processes and commercialization of product. And there's a big risk that we're going to miss out on opportunities to utilise their potential. At the end of 2013 and the beginning of 2014, I produced 2 policy statements on graphene and composite materials, highlighting the issues that these sectors faced. What was quite interesting about both of these industries, which they were actually facing the same problems, and it's these that I'm just going to sort of summarise for you now. The first of these, as we've already heard this morning, is very critical to our manufacturing process, supply chain. In 2010, BIS and UKTI commissioned a review of the composite sector to look at supply chain. And whilst it was identified that there were 1,500 composite businesses in the UK which were producing an annual turnover of about 1.6 billion, only 38 of those were responsible for producing 85% of all the composites output. The majority of companies were actually SMEs, and indeed and in need of support to develop cross-sector businesses and enable them to compete in a growing international market. But there continues to be a very siloed mentality within the composites industry, where companies see themselves as being part of a particular sector rather than being part of a wider composites community. This fragmented supply chain has been recognised as one of the biggest barriers to growth within the sector. It is vital that cross-industry practices and capabilities be made visible to all manufacturing sectors. This will create a national supply chain network that is flexible enough to cope with market shifts and requirements on a global scale. Supply chain is also key to ensuring the success of the UK graphene market. The matter of variable quality and quantity are still seen by many graphene producers as one of the biggest issues. And this leads to reticent industrial investment and an underdeveloped supply chain. It is essential then that an integrated academic and industrial programme be developed further to encourage scalable demonstrators, and in turn this will help develop the supply chain and provide industry with a greater confidence in the viability of product. Although academia continues to develop its knowledge and expertise in the field of advanced materials, UK industry is still not fully engaged in addressing the potential skills shortage, and this could cause particular difficulties with advanced materials products as they enter the market. Inconsistent training at both operator level and at the professional level, along with a reduction in the number of universities offering materials-related degree courses, has resulted in a poorly trained engineering and material scientists workforce. This could seriously affect the materials market in the coming decade and have a knock-on effect to UK manufacturing. A road mapping process is underway, particularly in the composites industry, to try and identify the technology needs of manufacturers and determine what types of composites they might require in the future. And there is a real need to ensure continuity of knowledge from research into industry. And there is a need also to be for a focused campaign to promote UK R&D to entice professionals into the field. The cumulative value of investment in UK graphene research has now passed the 1 billion mark, and realistic applications become ever more attainable. Considerable financial support has already been given to the UK by the UK government to fund academic research, but relatively little investment has been made in the commercialisation of graphene-based products. There is only a small number of companies in the UK manufacturing graphene, and most of these are SMEs. These companies predominantly specialise in the manufacture and supply of graphene-based materials and are not application design. Inevitably, the gulf continues to grow between early stage research and commercial mass production of both materials and product. Investors have so far been quite reluctant to provide financial backing to commercial ventures, mainly because they are of the view that products which are in direct competition with already well-established technologies are not worth the risk. So a kind of wait-and-see attitude has developed within the financial markets. Without confident investment to steer companies from SMEs to commercial independence, the UK position as a leader in graphene manufacture and other advanced materials will be severely impeded. Intellectual property. Now, this is a bit of a touchy subject with quite a lot of people. There have been a number of references to the patent thicket, making it very difficult for industry to get a foothold in the market. In 2013, the data that was available was approximately 7,500 patents were filed worldwide, most of these held by the Chinese, with the United States and South Korea holding the majority of the rest. It's sad to say that really only 60 patents have been filed by UK, despite the fact that graphene was invented here, shall we say. Now, I guess this could be seen as poor foresight by UK industry in not seizing the opportunities to copyright practical applications, or it could be that UK industry is much more discerning about patenting and only patenting applications that show themselves to be viable. Either side of the fence, wherever you sit, UK industry should consider its strengths and look to target applications that can be easily taken up by strong UK businesses, such as those in aerospace, biomedical engineering, automotive and defence. Likewise, we must ensure that the regulation of these materials does not strangle development or application, ensuring that flexible and realistic standards and guidelines are made available to industry. Of all of this, the environment actually plays a key role, and so I thought I would bring it up here. The sustainable management of waste forms the backbone of the government's environmental policy, and the composites industry is particularly keen to ensure that the amount of composite materials that are making their way into landfill sites each year is reduced, and this can be applied to all kinds of materials, really. It's therefore essential that the market for advanced materials, as it grows, methods of recycling and recovering these materials will have to be developed. To ensure the UK maintains a world-leading position on environmental issues, investment is needed to find more cost-effective recycling methods, as well as collection and separation infrastructure. And the use of bio and natural materials should also be encouraged across the manufacturing sector. Now, whilst I've focused on the obvious engineering issues, there is one area that is still often forgotten, that of engagement. We have to consider the views and opinions of the outside world as professional engineers. There have been several technology breakthroughs over the years that have offered the potential for step changes in the way that we live, but many have suffered from being overhyped by the media. This results in a very disappointed public when these material technologies don't yield the purported changes that they were meant to deliver. There has been considerable media interest in advanced materials, but much of it has been focused on the initial exploratory research and potential applications. To truly demonstrate these amazing materials' potential, a more concerted programme of public engagement is required to fire up the nation's interests. This should not only focus on what it is and what it can do, but on how UK industry and academia are leading the development of tomorrow's technology through product development and manufacture. So what's next? Well, if we're going to see these incredible materials develop and become commonplace in our factories of the future, then we have a responsibility to ensure that the UK industry overcomes these barriers. We need to establish collaborative groups to enable innovation and application to be developed simultaneously, whilst creating task forces to focus on mass production methods. We need to identify where advanced materials could be used and engage with research organisations, manufacturers and material suppliers to develop new applications and cross-sector standards. We need to address where our gaps exist in the skills base so that appropriate knowledge transfer and training can be provided. And we need to address the potential skills shortage and urge the catapults to continue to assist SMEs in developing technical demonstrators. With the industry, we need to work with industry to identify supply chain gaps and create supply chain networks, develop a coherent strategy for SMEs to get materials technology to market and protect UK IP. And finally, we also need to ensure that government and the UKTI need to continue their work to increase international exposure of UK materials markets, enable industry to compete more effectively in the global arena. We have to create a robust strategy to engage investors to help reduce investment risks, and we need to establish a robust public engagement strategy for advanced materials and other emerging technologies. So it's my belief that the future of advanced materials is definitely a strong one. We're on the cusp of a step change in manufacturing methodologies as a result of advanced materials. And the focus must be on designing manufacturing methods to mass produce these wonder materials. Industry and research is going to have to work much more closely together to ensure that the UK manufacturing industry is at the global vanguard. Thank you very much.